Thanks, everybody. It's really nice to be back in Santa Clara, where lots of cool things are happening. I'd like to take a little bit of your time and talk about, some tools that we've been using for post-wildfire sediment analysis and how we use them to kind of take this analysis and push forward into our design phases. This has become really important to us in the last decade or so as the company I work for, Natural Channel Design Engineering, has become involved in a lot of post-fire flooding issues. And, some of these issues affect, natural resources, and that's one important aspect. Some of these that we've been asked to work on actually affect the urban wildland interface, a lot of houses, a lot of infrastructure, and a whole nother realm of panic, if you will. So there's a lot of hurry involved in this, and so the tool that we've kind of rely upon to do a lot of this assessment is this WARSSS methodology. And WARSSS is the acronym, stands for Watershed Assessment of River Stability and Sediment Sources. It is developed by Dave Rosgen and his cohorts at Wildland Hydrology. You can find out a lot more about it than I can tell you on the EPA website. It's a methodology that is out there, has been approved for use, but probably underutilized as we've come to see. So, and I just want to talk about how we're using them. So post-fire sediment loads, they can overwhelm your infrastructure, they can overwhelm stream channels, destabilize those channels, because as those channels adjust to the new reality of the watershed, which is a lot more water and a lot more sediment being transported through. And so what we're often asked to do is reduce those sediment loads and increase the stream stability. And much like we're doing in Santa Clara. The key to this reduction is to first understand where your sediment sources are coming from, and also understand a lot about where that transport is coming from. And as you'll see, the transport becomes a really critical issue as you're going into watershed restoration. And these practices that focus on watershed restoration can help you kind of speed up the watershed recovery, something that could take many, many decades. If you are diligent about it and work rapidly, you can turn that watershed around in a matter of a decade or so. So, and these methods kind of lend themselves to utilizing this, natural channel morphology, natural materials, and all of the kind of cool methods that people have been talking about so far, and get you back to a proper functioning watershed. And the key aspect of this is one of the key aspects is understanding where the sediment source is coming from. Is it hill slope processes, or is it a channel process? Because if you are actively trying to fix something or enhance something, you need to know what process you're working on. Okay, hill slope, channel, two big important resources, and they take different methods to work on. So, channel condition, when we're talking about channel processes, is a key element. And I'm just throw this up there. This is some data looking at sediment rating curves for good condition channels versus poor condition channels. Poor condition, steep banks, eroding banks, incisions, those types of things. And really what it's just pointing out is that these poor condition channels, because they have so much more sediment, with the same amount of water, they can transport so much more, orders of magnitude more. And so that channel condition is a really key factor here. And 10 tons versus 100 tons per linear foot of bank is a big deal. So So a little bit about this watershed assessment of river stability and sediment supply. It has two major portions of it. One is looking at sediment sources. And we're looking at sediment sources from, and we're trying to divvy this out from the two major sources of sediment in the watershed. One is coming from those channel sources, and we use the Banks model to look at that. And the other is for hill slope or road processes, and we can use the Ermit model to utilize that. And with that, you know, going over the whole watershed, you can model kind of the total magnitude of sediment from these different processes, weigh them out in their relative ways, understand what the major sources are, and where you need to put your limited time and funding towards addressing that. Okay? There's channel and valley classification helps with that source as well. The main thing about the Banks and the Ermit models is they're really compatible because they provide an average annual sediment yield. These are not storm-based like the Moosley or those kind of things. They're average annual, and so they do lend themselves to this natural channel design approach developed by Roskin and others that kind of works on an average annual flood basis and those things. The next big important part of the WARSSS is looking at sediment transport. And we're looking at sediment transport through those channels. When we get a supply, it comes into the channel, how much of it can be transported through. And that transport is based upon the channel shape, the channel slope, and roughness and a lot of other things. So what you're trying to do is look at how much more water you have coming in, how frequently that comes through, and then route the sediment through with that new amount of water given the specific channel shape. This is also helpful because channel shape is one of those things that we can manipulate. It's one of the few tools that we have when we're working in this condition, and that's what people have been talking about all morning, is how do we change the shape of the channel to do what we want it to do. Some cases, we might want it to transport more sediment than it's doing now. In some cases, we might want to do less, okay? So this is a methodology for, you know, we use the channel type and valley types to map a basic structure of channel functions. So this can be started in a GIS-based. We look at Roskin channel types. We look at the valley types that support them, whether they're big, broad valleys or much confined valleys, what those valley slopes are, so we understand what kind of streams can be stable there, and then we look at what kind of streams are there. And this can be done really quickly in a GIS-based approach, and you can start to target areas of a large watershed that are going to be most susceptible for sediment supply and transport, the things you're interested in. So it's a way to really quickly whittle down a big area and a big problem into smaller chunks that you can look at. Then you can apply this Ermit model, which is it's a web-based model that's easily available on the web, and you compare that to your Banks model, and I'll talk a little bit about that, and to estimate those key sources, whether they're hill slope or channel slope processes, okay? Then you can also utilize this flow-sed, power-sed modeling, which is in the Rivermorph program, to estimate typical transport quantities in tons per year and look at for opportunities to restore channel function, either stopping that transport or increasing it as needed. So there's a lot of stuff going on here, but what I'm trying to emphasize is that this can be done really quickly. Okay, this is, while it's data intensive, it's data that's pretty easily collected and collected quickly. And so you can move through this process rapidly. When we first applied this, almost 12 years ago now, we had a 25,000 acre fire that we had to look at, 9 different watersheds. 65 different miles of channels and reaches. And with a moderate-sized field crew of 5 people, we had all the field assessment done in 2 weeks. In another 2 months, all the analysis was done, and by the next season, we could start on design and implementation of those. So you can rapidly get a handle on seeming unsurmountable problems and get going. But the key to this is, these kind of natural channel design principles. And the first one, the most important one, is that your form is roughly equivalent to your function of your channel. If you understand the channel shapes and you understand the valleys that surround them, you can rapidly measure those and estimate what the function of that's going to be, as in wide, shallow channels are very poor at sediment transport relative to narrow and deep channels because of the shear stress distribution in those. So we're looking at the active channel for sediment transport. We're looking at floodplain terraces to carry the high energy of those high flows. And we're looking at the bed forms and meanders as a way to dissipate energy. That's part of that natural channel design principle. And it's part of what goes into this assessment. But it's a visual assessment, so you can do it quite rapidly with a trained eye. These channel types that we're looking at, basically we're utilizing the Roskin channel classification method. It's a visually based thing, but it's measurable. You go out, you can visually assess a reach, then pick the typical riffle portions of that, do your quantitative measurements there, make sure your channel types are good, and then you can start looking at dividing those channel types out into roughly what are going to be, relatively stable channels versus those channel types that are not. And here, A, B's, and C's, relatively stable channels for most part, and then the F's and the G's are not. F's are laterally unstable just because of their form, big steep banks. They want to carve away at those banks, and their shear stress because of the flat channel bottom is aimed right at the toe. So those are high sediment source from their banks. The G's are, think of gullies, and they want to incise, and they are unstable vertically. They want to sink really quickly because they have no floodplain in order to dissipate that energy at high flows. So those are both high sediment sourcing channels. And when we find those areas, we kind of zone in on those. Okay. D channels are another aspect altogether, and they are unstable, but they can aggrade sediment. They don't pass it very well, and so this is of use to us in the future. So here's just an example map of something that we created following the Schultz fire back in 2010. We visually assessed all of these channels, about, like I said before, about 65 miles worth. Did it pretty rapidly. This was a 15,000 acre burn, and unfortunately, this is on very steep slopes, and all of this stuff down on the right side of the map there are houses. It's a pretty dense housing development with absolutely zero drainage and built into the infrastructure, and the increase in flows and sediment was tremendous for them. That's how we got started on this work. So a little bit about this bank erosion hazard index. Once you've identified that you have channel reaches that could have high bank erosion, how do you measure that? And how do you quantify that? Well, the bank erosion hazard index allows you to visually assess the erodibility of banks. It's based upon bank angle, bank composition, as in what the soil type is in there, how much rooted material there is in there, and whether there are certain breaks in that material and stuff like that. You can provide a categorical score for bank erosion. And you do this for a typical reach. Could be 50 meters long. It could be 500 meters long, depending upon the homogeneity of your channel. So you take that, both sides, and you have a bank height, and then you can look at what the near bank stress is against that, looking at the channel form and visually estimate near bank stress. Again, put that into categories. And this, the Banks model provides these curves. And you can look at bank recession rate, okay, based upon your bank erodibility hazard index. Okay, you break those up, use those different curves, look at the near bank stress categories, and you can roughly quantify your bank recession rate in feet per year. Take that feet per year times the height of the bank times the length of the bank, and you get a cubic yards per year, which you can change to tons per year pretty easily. You can map all of this out, okay, and look at entire drainages as tons per year coming out of this, and it breaks down to various reaches. So you can see where the high sediment source reaches are and where the high sediment source channels are. You can compare that to the hill slope erosion in each of those sub-watersheds that feeds those reaches using the Ermit model. This takes some time to sit down and kind of work through. It's computer-based, but once you get the hill slope, the soil type, burn severity, and vegetation types, you can plug that into the Ermit model and kind of rapidly go through this and break these up. So for this, these maps here, these compare, you know, our hill slope erosion rates on the left side of the channel from the Ermit model, and then looked at our bank erosion rates for the same reaches, the receiving reaches. And this is part of the museum fire, which we worked on a couple years ago, just again, right above some heavily populated areas. And these amounts of sediment were getting delivered to the town and kind of filling up people's yards and houses. They were a little upset. So compare all that stuff, and then you can start looking at where the sources of sediment are. Most of the work that we've done over the last 12 years or so, and because there are exceptions, but most of it leads us to the highest percentage is usually coming from channels. The hill slope processes, because the Bayer teams do a pretty good job at stabilizing hill slopes, but are kind of minimal compared to what can come out of these channels, especially if they've been incised deeply and are unstable. If you were fortunate enough to not get a big flood right after a fire, you're probably going to have more sediment coming off of hill slopes than you do there. Two different sets of practices to address that sediment source, okay? And so at this point, you have a really good decision tool in your hand that says, we need to do bare treatments, we need to do planting, we need mulch, we need stabilize the hill slopes however we can, or really 85 to 95% of our real problem with channel stability is in the channels themselves, and then we should focus on that. So this is, again, some examples of what we have experienced from both the Schultz, the museum fire, and now the pipeline fire, that these are what those eroding channels look like after they've been incised, okay? These were pretty small, 2 or 3 feet deep, and now they're 10 feet deep or better. All of this material is supplying to the channel, and it doesn't take a whole lot of water to mobilize it. We're not talking about big floods. We're talking about a 1-inch rainstorm on this fire burned area that can bring a whole ton of sediment down. So once we look at those, in a lot of cases, you look at those numbers, and the sediment source numbers are absolutely